Oops. All right, remember, missing exams or quizzes, make sure you get them in. You know, at least get half credit. The solutions are already online, so it's easy to do. All right. You don't want to have to take this class again just because you didn't turn in your work, you know. If you get everything turned in and do well in the final, you should still be able to pull a decent grade in this class, no matter how far behind you are. All right, let's look at exam 22 here. First, let's move number 2 out of the way. So we have a rocket carrying fireworks is launched from a hill above a lake. The rocket will fall into lake after exploding at its maximum height. The rocket's height above the surface of the lake is given by h of t, where h is in feet, t is in seconds. You can see just by looking at the height, if you plug in 0 for time, that you get 80. So what we're looking at is there's a hill at height 80. Now this thing might look like this, or it might look like this. If we find out the axis of symmetry or use the vertex formula, we'll find out where the peak is. If it's over here, it's going to look like that. It'll go up and back down. But if it's over here, it's probably going to do that. So let's find out, how long will it take for the rocket to hit 128 feet? Well, assuming it does reach that height, that tells us that we're looking more like something like this. It could go higher. Let's move this down. If it goes higher, that means there's going to be 2 different times that it reaches that height. So let's find out. If we take our height, let's scoot this over a little bit, h of t, so we take our height and we set it equal to 128 feet, and now we solve for the time. We'll find out. So to solve this, the first thing we want to do is put it into standard form. So if we subtract 128 from both sides, we get what, negative 48 here. All right, the next thing we want to do now that it's in standard form is solve for t. I'm looking at this and I think all of these numbers are divisible by 16. In fact, let's divide both sides by a negative 16. All right, this is still going to be 0. So over here, we just get t squared. And 16 goes into 64 4 times. Minus there. And into 48 3 times. Okay. Put that. So this, I think we can eyeball factor this thing. We could use the quadratic formula. But let's see if we can just factor it here. Oh, this is part A. So let's see, what, a -3 and a -1. All right, so either t -3 is 0 or t -1 is 0. So this tells us that t is 3 seconds. This tells us that t is 1 second. So at 1 and 3 seconds, this thing is going to reach 128 feet. So we're looking at something like this. There's 1, there's 3. So that's part A. Let's look at part B now. Move this up a little bit. Oh, I lost a mark here. I wonder where that went. I don't know. That's all right. So how many seconds after it's launched will the rocket hit the lake? Well, it hits the lake when the height is 0. So let's take our height here and set the height equal to 0. So I think, again, this is already in standard form, but if we divide both sides by -16, we get t squared minus 4t minus 5. 16 times 5. How many times does 16 go into 80? I think it's 5, right? All right, so now we can factor this. I think we can eyeball this one too. T minus 5 plus 1. So this tells us either t is 5 from here, or t is minus 1. Again, these are in seconds. So we're not really concerned about negative time. So this 5 seconds is whenever it hits. So what we're seeing here is boom, 5 seconds. That other one is telling us that if we went back in time, it would have hit the base of the hill, I guess. Okay. So we don't know the maximum height. They never asked us, but we could find that out using the vertex formula. All right, and we can put some happy red boxes around our answers. Okay, so that's number 1. Let's look at number 2. Bring it down here. All right, I guess there's no instructions for number 2. My bad. I'm guessing they want us to solve for x, right? I mean, if you just write that down and don't give any instructions, what are you supposed to do? You know, you can do anything you want, technically. Be correct. But it's kind of implied, solve for x, right? So the first thing I do is get rid of these fractions. So I look for the smallest number that all these 3 numbers divide into, which I think is 24. So if we multiply everything by 24, 24 over 3 would be 8. 24 over 12 would be 2 times 7 would give us a 14. 24 over 8 would be 3 times 5 is 15. Now we need to put it in standard form, meaning make everything equal to nothing by subtracting 15. So we have everything equals nothing now. And now we need to factor this. This 8 is kind of making it difficult. I mean, we could use the quadratic formula, right? You can always do that, but I think it'd be faster to use our little trick here. Let's see, what is 8 times 15? Need my calculator. Sounds about right. Yeah, 120. So we need 2 numbers that multiply to give us 120. They need to add to give us 14. So what do you say, 20? Yeah, this is a negative 120, isn't it? Yeah, so 20 and negative 6. So those numbers tell us how to break this thing up so we can do our grouping. Factoring by grouping, I think is what this is called. So we rewrite the 14x as a 20x minus 6x. That allows us to group. We'll look at these 2 groups here. So out of the first group, we can pull out a 4x. That gives us a 2x plus 5. Out of the second one, we could pull out a minus 3. That gives us another 2x plus 5. So we have a 4x and we have a -3, and they're both being multiplied by a 2x plus 5. So now that it's factored, the zero factor property says we can just set each of these factors equal to 0. So this equation is equivalent to these two equations. So this one tells us x is 3/4. This one tells us x is -5/2. Boom. Any questions? Everybody's out in Zoom land. All right. Yeah, if you hadn't have come, I could have zoomed from home. No, this is fine. I'd rather be here. All right, so we have quiz number 23. All right, let's pick out some of the hardest problems in the book. All right. Where's the next? Okay, I'll go backwards in time then. Let's see. In the blank, we did that one, right? Now let me find the next homework section. That'll be fun. We haven't done vertical asymptotes. So, So let's say solve for x. Throw you in some easy ones here. Let's try this one. And this one. All right, both of these have x squareds in them. So this one, you're gonna have two solutions. This one is a cube, so you're gonna have three solutions here. So this one, yeah, you could use the quadratic formula, or you can use the zero factor property. This one, you can still use the quadratic formula, but you'd have to do something first to set it up because you have an x cubed here. All right, we'll take 15 to do this. So at 11, we'll work these together. I'll put y'all in breakout rooms out there. Y'all can collaborate. All right, let's look at number 1 here. So this first thing is put this thing in standard form, right? We'll put the highest power of x first. Move this 23x squared over. Oops. So now it's standard form. The first thing I notice is that everything has an x in it. I'm looking at the numbers and 23 is prime, so I can't really factor out a number. I could also pull out a minus sign. I just don't like a minus being out here. So I'm going to factor out a minus x. So we get a 4x squared plus 23x plus minus 6 equals 0. All right, so now I have something I could use the quadratic formula on if I wanted to, and then this. Of course, I can multiply both sides by a minus. Okay, so clearly if x is 0, doesn't matter what that is. So x equals 0 is one solution. But let's go ahead and factor this thing. All right. Because that 4 is there, I can't really eyeball it. So let's use our trick here. A times C is a -24. B is 23. So we could do -24 and 1. No, +24 and -1. Yeah. So we're going to take this 23x and rewrite it as 24x minus x. Now we're going to group. We're going to look at each of these groups separately. The first group we could pull a 4x out of. That would give us a 6x. Wait, no, that would give us x plus 6. And the second group I'll pull a -1 out of, which gives us the x plus 6 again. So I have this x here. I have a 4x and a -1, and they're both being multiplied by an x plus 6. So we have three factors, either x is 0, 4x -1 is 0, or x plus 6 is 0. So this tells us x is 1/4. Tells us x is -6. So here are our three solutions to this third order polynomial equation. Now for number 2. First thing, let's put it in standard form. We have a -2x squared minus 3x plus 5. Okay, I'm going to multiply everything by a minus sign. So we get a 2x squared plus 3x minus 5. You don't have to do that. I just don't like dealing with minuses up there. So that makes it hard to eyeball factors. So we'll do our trick again. A times C is -10. B is 3. So we could do +5 and -2. So that tells us to take this 3x and rewrite it as 5x minus 2x. So this one we can pull a x out. We get a 2x plus 5. And then we'll pull a -1 out of this. We get a 2x plus 5 again. So we have an x and a -1, both being multiplied by a 2x plus 5. Well, did I miss something?
Well, all I do, I just put them in descending order. Squared.
Yeah. I just multiplied everything by a minus sign.
Oh, so you're both negatives.
Yeah, I just don't like minus signs. No, you don't have to. It'll work out the same.
I had a question about this one. If I have negative, but if I can see- I'd like to see like -4x.
It should be a positive one. We shouldn't get different answers. So one of us did something wrong.
I could have put
Yeah, you have a minus sign. What's going between? You have that 1 times x plus 6. Before the 1, you have a plus or a minus. Where is it? It's an invisible plus sign. Okay. Yeah, I think you're off by a minus somewhere.
put -4x.
Let's see. This would be. It'll be a positive, positive, negative. Yeah, you're missing a minus sign somewhere. All right, back to this one. Now that this dude is factored, we set each factor. equal to 0. This tells us x is 1. Tells us x is -5 halves. All right, you know how to check, right? Yeah, plug in -1/4 and see if both sides of the equation match.
I think I did do it wrong, 'cause I got a positive one.
Okay, well, that's what I got.
I think that's,
Yeah, you can always check your work. You take that and you plug it in for x and make sure both sides of the equation are equal. So on the final exam, you'd want to check all your work, right? Make sure it's right before you submit it. All right, that's it for the quiz. Now we are on page 157, I believe. Oh, I'm gonna have to fit all these on one page, I think. Oh, let's see. Okay, how many real roots are shown in the graph? All right, well, number one here, there's 3 of them. Right here, here, and here. Those are the real roots, because that's where they cross the x-axis. The real roots are 0, 1, and 2. If I wanted to reconstruct this a function for this graph, I could do x minus 0 times an x minus 1 times an x minus 2. This is a possible function for this graph, because we could also have something like this. All right. All right. All this does is tell us about where it's crossing. Okay. Actually, because this 1 here just touches, we would have to square that one. Okay. So where it crosses, you get x minus that solution. If it just touches, it's squared. Remember, if you had remember x squared, if you graph that, it does this. It just touches right at 0, right? This is 0 if you make x 0, right? Remember, if it just touches, you're getting that solution twice. So basically, this one has 4 real roots: 0, 1, 1, and 2. Okay, it just depends on how you want to count it. All right. So this one happens twice. So 3 or 4, depending on how you want to count them up. Okay. The minimum possible degree of the polynomial. All right, this would have to be a 4th degree polynomial. All right, so we'll say that there's 3 real roots, 0, 1, and 2. 1 happens twice, so we won't count it twice. But the minimum degree of the polynomial would have to be a 4th degree. So you get an x squared here times an x times an x. So it's going to be a 4th degree. Okay, so when it touches, that means you're getting that root twice. So a possible equation for the function in factored form with the minimum degree, this is a possible function. All right, it's not the exact function. We don't know, because what if this thing did this? All right, that would be a different function, right? Because you could have a 2 out here, or a 3 out there, or a 4 out there. Remember, if you multiply your function by a number, that would just stretch it vertically. Okay, so that's why they asked for a possible equation. So on number 2 here, each one of these roots, they're crossing. We have root crosses at 1, 2, 3, and 4. But each time they're crossing, so a possible function for this would be x minus 1 times x minus 2 times x minus 3 times x minus 4, right? Where it's crossing the x-axis, that's where the function is 0. You see, if I put a 1 right here, this is 0, and it doesn't matter what that is, we would get f of x equals 0. Does that make sense? Why, if we know the roots where it crosses the x-axis, we can just do x minus each root and multiply them together, right? We could multiply this all out if we wanted to. Okay, so yeah, if I put a 2 right here for x, this is 0. 0 times anything is 0. All right, that's why everywhere it's crossing the x-axis, that's where the function is 0. Right here, you haven't gone up or down. That's where the function is 0. So where it crosses, you just write it down. Over here, again, this one just touched at 1. So we had to square it. When it just touches like that, that means you're getting that same root twice. So this one over here on the right, this one is also a 4th degree. You get an x times an x times an x times an x. You're going to get an x to the 4th. Okay. Remember, whenever you draw these things, the more wiggles it has. See, an x squared crosses twice, right? An x cubed is going to cross 3 times. An x to the 4th is going to cross 4 times. All right. Every time you raise the power of x, you get an extra wiggle in there. So let's look at a couple more examples. All right, this one, our roots here are at -2, and it's just touching, so we get it twice, and then over here at 0. So we would say it has two real roots. This one has multiplicity 2, okay? So this would be a 3rd degree. And a possible function would be x minus a -2, x minus, here, I'll just square it. And then an x minus 0. You just do x minus each solution. Because this one happens twice, we have to square it. All right, so you see you got an x squared times an x, that'd be x cubed. And again, this is a possible one because this, another version, if I put a 2 here, that would make this thing twice as tall, right? So we don't know what this number is out front. We could just put a. But it has to be something like that. That's the form of the function. So number 4 here, we have another one touching here at -1/2. And since it's touching, we have to say it happens twice. And then over here at 3. So we have 2 different real roots, -1/2 and 3, but it's going to be a 3rd degree polynomial because you have to count that one twice. So a possible function here would be x minus a -1/2, and it happens twice, and then an x minus 3. So that's a possible function. The general function, there's going to be some number out here. It depends on what this number here is. We don't know how big that valley is. I'll put it. That's some number. They don't see, they only gave us numbers on our x-axis. We don't have any sense of scale on our vertical axis. This could be 1,000 or 1,000,000, or it could be 1, right? They didn't give us any sense of scale on the y-axis, so we don't know what this number out front is, because again, that number just takes your graph and stretches it vertically. All right. Make sure I remembered. So prepping for rational functions. This is where you put a polynomial over a polynomial, is what a rational function is. Something like x minus 1 or x squared minus 1 over x plus 2. You put a polynomial over a polynomial. Okay, remember a rational number is a number over a number, rational number. Well, now we're looking at rational functions, okay? But to lead up to it, determine whether the fraction is 0 or undefined. You cannot divide by 0. So this is undefined. 0 divided by 8 is 0. This thing, you're getting 0 on the bottom. undefined. This one, you get 0 on the top, so that's just 0. Yeah, that means undefined. Undefined. Here's my legend here. All right. That's what that means. Can't divide by 0. All right. To remind you why, let's look at the graph of 1 over x. Something like that. So if I put a 0 right there, right, what happens right here at 0? Well, it depends on how you get to it. If you approach 0 from the right, this thing goes to positive infinity. If you approach 0 from the left, this thing goes to negative infinity. So 1 over 0 is both positive and negative infinity. And there ain't anything that's more further apart than positive and negative infinity. All right, so you can see it. The way we deal with dividing by 0 is we look at numbers really, really, really close to 0, right? If I put in 0.000000001 for x, then f of x is 100 million billion 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 or whatever. But if I plug in negative 0.000000001, then f of x is negative 100 million billion zillion jillion. You see what I mean? These are two numbers very, very, very close to 0. One's positive, one's negative, and they just keep getting further and further apart. So that's what calculus is about. We take limits. We look at the limit as x approaches 0. Here, the limit wouldn't exist because they go in opposite directions. If I had something like this, where approaching 0 from both sides, you got infinity, we would say the limit exists and it's positive infinity. But here, you get two totally different directions. Okay. Limits. If I had a function like, let's say this is a 1. If I had a function that did this, it got closer and closer to 1, I'd say the limit of f of x as x goes to infinity would be 1. Because as I go to the right, this thing gets closer and closer to 1. So that's calculus, limits, and dividing by 0. Specifically, calculus is more like, we know how to find the area of a triangle. We know how to find the area of a rectangle or a square, right? But how we deal with the area of this, right? Well, what we do, calculus, is we break it into a whole bunch of rectangles. Okay. Something like that. Here's the gist of it. And then we know, like, for this thing right here, this would be like an x1, and then this would be like f of x1. So the area of that rectangle, so I'll put x2. This would be length times height, right? I'd say x2 minus x1, that's this length, and then multiply it by the height, and that would give me the area of that rectangle. And then I just do all of that. Remember I showed you the sum formula? So I sum over the area of all of these. But you see there's an error. You're missing a little bit here, right? So what I'm going to do is I'm going to call this little thing, I'm going to call it triangle x. That means change in x. Okay. So each one of these rectangles has the same width, change in x, change in x. All right. So all these areas add together, I would sum, it would be f of x times change in x, something like that. All right, so you get the height at each spot times the same width. All right, and you just sum up over all of them. But then what we do is we take the limit as this width gets smaller, because the smaller you make the width, the less error there is. So if I made these like twice as small, right, I'd be like, See how now I lost some of that error? I just have twice as many. All right, so boom, it'd be filling in all that error, right? So I'd have twice as many, right? Well, what you do is you let that width go to 0. So what you end up with is an infinite number of rectangles that are all infinitely thin. And then that error that's not taken into account goes away. So that's why the concept of limits are useful in calculus. That's your step 1. So you look at an infinite number of rectangles that are all infinitely skinny. And even though there's an infinite number of them, you'll end up with the actual area. Well, that's how do you get the area of the little tiny boxes, the missing part, that's how you get them. Right? Because no matter how small you make it, there's still a little bit of area. But if you take the limit as that little width goes to 0, no, it gives you exact, yeah. See, that's it. In computer science, though, you can't deal with infinity. You can only do that in pure math. So in computer science, it's always going to be an approximation. You can only do a finite number. It just does, several hundred billion of them. And there's other things in pure math where you can't get an exact answer, but there's algorithms in pure math where the more iterations you do, the closer your answer is. And then you can prove that within this many iterations, you get within this close to the actual, answer.
Yeah.
All right. So this is calculus. I had to, throw something in. This lesson here is pretty simple. Don't divide by 0. That's it. We're going to do pages and pages of don't divide by 0. All right, decide if the equation is linear or quadratic. We only have x to the first power. That's linear. Linear, linear, linear. Find all values of x which make it true. Well, nothing's squared, so everything's linear, right? This, you'd have to plug in a 7. Here, a -3. For this one, we'd have to plug in 9/2. This one, we'd have to plug in a 7/4 for x. When they say find all values of x which make it true, they're saying solve for x, right? That's what it means. Solve for x means what values of x does this equation actually hold? Now these are all quadratic, right? So everything has an x squared. So this is quadratic, quadratic, quadratic. So what values of x make it true? Well, we have to solve for x. So to solve for this one, we could eyeball factor x plus 1 plus 1. Guess what? That's the same thing as x plus 1 squared. This obviously is only true for x equals -1. This one here, we'll have to do our trick here. Some of y'all might be able to eyeball this. This is fairly simple. But if we do our trick, a times c is -2. B is -1. So two numbers that multiply to give us -2, that add to give us -1, 2 and 1. So we would rewrite this thing as 2x squared minus 2x plus x minus 1. So we could factor out a 2x and we would get an x minus 1. And over here, we'll factor out a 1 times an x minus 1. So we can see it's a 2x plus 1 times an x minus 1. So either x is -1/2 or x is 1 by looking at the factors. Over here, we'll do the same trick. A times c would be a -42. B is 11. So our two numbers here, two numbers that multiply to give us -42 but add to give us 11. So set. Let's see. Find out. 42 divided by 7. We have 7 and 6. Oh no. Okay, one's got to be negative and one's got to be positive. 2 divided by 3. 3 and 14. So if we do 14 and negative 3, so we could rewrite this thing as 2x squared plus 14x minus 3x minus 21. Then we can factor out a 2x, get us an x plus 7, and factor out a minus 3 and get an x plus 7. So we have a 2x and a minus 3, both times x plus 7. So the first factor tells me x is 3/2. The other one says x is minus 7. So those are the values that make it true. So notice the quadratics, there's always two solutions. This one is -1 twice because it's squared. Remember, when a thing's squared, what this thing looks like is over here at -1, it touches. Boop. All right, so 159. Oh, that's the other thing about calculus. I showed you there's areas, right? What about slope? Right? We y'all learned about slope, right? Rise over run. Well, this thing has a different slope everywhere, right? So turns out, let's say you have f of x equals x squared. I'll redo this. X squared looks like this, right? Well, what's the slope? Well, the slope is different at every point. So the slope we'd call f prime of x is 2x. I'll tell you right off the bat. So the slope depends on what x is, right? So right here at 0, the slope is 0. You plug a 0 in, you get 0, right? But over here at say 1, the slope is going to be a slope of 2. So these are called tangent lines. You have a straight line that's tangent to a point on the curve. So the slope of the tangent line is the same as the slope of the curve at that point. So there's a relationship between the area here and the slope. Okay. So this is called, if you take the derivative of a function, you get the function that tells you its slope. The opposite of the derivative is the integral. You take the integral, all right, you get the area. So you'd say from A to B. So like if this was like A and this was like B, the integral of the function would give you the area underneath the line. And these are opposites. So if you take the derivative of the integral, you get the function back. If you take the integral of the derivative, you get the function back. So slopes and areas are related. So if you think about it, the area of a circle is pi r squared. Well, the derivative of the area is 2 pi r. That's the circumference of the circle. All right, so the length around an object is related to the area that it encompasses. Okay, circumference area. This is specific for a circle though. Okay, which is useful. Okay. Let's put that up here somewhere. Circle. Anyhow. All right. Answer the following. Graph x equals 2. X equals 2. Well, here's x equals 2. I guess I could just draw the line there. That's x equals 2. Every point on that line has an x value of 2. What is the slope? What is the slope to that line? What's the opposite? Undefined, right? The slope is change in y over the change in x, right? The change in x, we're not going right or left, right? Remember, a slope, a horizontal line, the slope is 0, okay? If I go at a 45-degree angle, the slope is 1. And, right, the more I'm going uphill, the bigger the slope is, right? Well, this line is going straight up, so the slope is positive infinity, but it's also going straight down, so the slope is also negative infinity. So the slope here is undefined. It's both positive and negative infinity, okay? What is the x-intercept? It crosses at x equals 2, right there. The y-intercept, there is none. It never crosses the y-axis. Now for a graph, y equals -3. Well, this line here, all the y values are -3. What is the slope? Change in y over change in x, all right? The y never changes. You see that? It's always -3. Change in y is 0. So the slope is 0. This is a horizontal line. You're not going uphill, you're not going downhill. It's 0. The x-intercept, there are none. The y-intercept, that y equals -3. Every point on the line is y equals -3, including when x is 0. All right, determine which of the following is a vertical line. All right. X equals 5. Let's look at A here. X equals 5. Boop. That's a vertical line. All right. B, y equals 5. 1, 2, 3, 4, 5. It's a horizontal line. 2x equals 8. That's the same thing as saying x equals 4. So that's a vertical line. D, y minus 8 equals 0. That's the same thing as saying y equals 8. So that's a horizontal line. This one, let's see, if I subtract, what is this, E? This was D. If I subtract a half from both sides, and I multiply both sides by 3 halves, I get x equals 3/4. So E is the same thing as 3/4. This. Basically, so yeah, that one's a vertical line. Basically, if all there is an x and there is no y, you have a vertical line. All right. So that one's a vertical line. X equals 0, right? J, that would look like this. Every value has an x value of 0. See, if you have an x and a y like that one, remember you can put that into y equals mx plus b form, right? So you're going to get some kind of slanted line. If you only have a y, all right, this is going to be a horizontal line. This one only has a y, so it's only going to be a horizontal line. This one's going to be a horizontal line. If you only have an x, you get a vertical line. It's when you get both x and y that you get something in between the two, right? The height depends on how far you've gone right or left, right? If there's only a y, right, it doesn't matter how far you go right or left. It's the same thing. So like this one here, y equals 5. It doesn't matter what x is, y is always 5, okay? So that would be like that one. All right, let's take a break, y'all, and then we're gonna look at 1/x in detail. So break. We'll resume at, let's see. Resume at 11:50. There's 13 minutes here to chill. The what? Thought we were in a recession. I thought we were. Seems like we're always in a recession. I mean, prices just went up 20% last week on everything. Oh, good. Dope. All right, rational functions here. So the simplest rational function is 1/x. So if you remember, we started off with simple functions. We said, what about x? That's the simplest function, right? It looks like this. And then we went to, well, what if we multiply it by something? And then what if we add something to it? And then we have all the possible linear functions. They look like this. It could be up here, just straight lines. And then we're like, hey, what if we have x squared? Right? So x squared looks like this. And then we're like, hey, well, what if we multiply it by something? Well, then that stretches it, right? And then it's like, well, what if we add, what if we add something to that? Well, then that moves it up or down. All right. And then what if we put a linear part to it? What if we do this? Well, then that part moves it right and left. All right. So now, and then we looked at what if you have, we didn't really graph them so much, but we kind of did. We looked at x cubes and x to the fourths and things like ax to the fourth plus bx cubed plus cx squared plus d. And we saw that those look like this. And the more x's you have, the more curly cues you have, the more it wiggles around. All right, so that's the evolution. Start off with the basic and then look at all the possibilities, linear functions, quadratics, the most basic one. And then we looked at all the possibilities. Then we looked at higher powers of x, and we kind of got into that a little bit. We saw the higher power of the x, the more wiggles you get. So now we're looking at rational functions. So now we want to look at, like, you know, something like x squared plus 1/x minus 3. So we're putting, like, basically a function over a function. All right. So now we're just looking at fractions of functions. And the simplest one is 1/x. All right, where you have an x on the bottom of the fraction. That's rational. So they want us to plug in these numbers. So 1/x, f of x, 1/1 is 1. 1/0.1 is 10. 1/0.01 is 100. 1/0.001, you see the pattern here. 3, 4, 5, 2, 3, 4, 5, 6. So what we're looking at is, here was 1. We found we got 1. All right. I guess I should put this somewhere where I can see it a little better. All right. So we found that as x gets closer to 0, f of x gets bigger and bigger. So as we go closer to 0, this thing gets bigger and bigger. Okay. Move that over here for now. Now, what about on the right side of 1? What if we do big numbers bigger than 1? Well, 1/1 is still 1, right? 1/10 is 0.0, is 0.1. 1/100 is 0.01. 1/1000 is 0.001. And then you see the pattern. 3, 4, 2, 3, 4, 5, 6. So what this says is, as x gets bigger, meaning as we go to the right, the function gets smaller. So we go down like this. So that's what 1 over x looks like in quadrant 1. Okay. So let's, maybe it's in this book here. Hold on. Maybe they give us an actual graph of it. No, we'll graph it on here then. So we found 1 over 1 is 1. As we get closer to 0, this thing gets closer to infinity. As we go to the right, it gets smaller and smaller. So that's what 1 over x looks like over here. Now, what about over here? Okay, well, if we plug in values that are negative, 1 over a negative number is a negative number, which means we're going to be down here. So if we plug in anything that's negative, 1 over a negative is negative. So we're going to be down here. And basically, you're going to get the same thing. 1 over -1 is -1. So as you get closer to 0, 1 over something small gives you something really big, but negative. 1 over something big gives you something small, but negative. So this thing is symmetric. It's symmetric about the line y equals x. It has that symmetry. If you flipped this over y equals x, you get this. So 1 over x has a symmetry. So now, one thing I would also need to point out is right here, right down the middle at x equals 0, they call this an asymptote. All right. In this case, it's called a vertical asymptote. Vertical asymptote. That means the function gets closer and closer to that dotted line, but it never touches it. Okay. So notice x equals 0, 1 over x. You can't plug 0 in. That's undefined, right? That's why there's a vertical asymptote at x equals 0. The function never crosses x equals 0. It can't. So if you plug a 0 in here, you get undefined. So that tells us something about these other functions. So let's look at a little more sophisticated things here. So this guy here, if I put a 6 down here, I would get 0, and you can't divide by 0. So this thing has a vertical asymptote. Asymptote at x equals 6. All right. You cannot plug 6 in. So that means somewhere over here at 6, there's this dotted line. Now, I don't know what this function looks like. It could be this. I don't know. But I do know it can't cross that dotted line. Okay. And they ask the domain. Remember, the domain is all the numbers that you could plug in where the function actually gives you something back. So the domain here is everything except for 6. So there's several ways of writing that. I could say all real numbers except for the number 6. So this is set notation. Squiggly brackets mean here's a set of numbers. So all real numbers except for 6. Or I could say from -infinity to 6, union 6 to +infinity. Notice these are round brackets. That means all these numbers not including 6. You see, if I did a square bracket, I would include the number 6, but I want to say everything but 6. So this is the same thing as this. Okay. Or I could just say x not equal to 6. So that's another way of saying it. So the vertical asymptote is at x equals 6. That's the function for this dotted line at 6. All right, but for the domain, I say the exact opposite. X can't be 6 because you cannot divide by 6. Okay. So this one over here, we have to figure out what numbers give you 0 on the bottom. In order to do that, we want to factor this. We want to rewrite this as, because if we factor it, we can just look at it and know where the zeros are. So if we try to eyeball this, we could do -8 and a +2. Yeah, so I could tell you right here, the vertical asymptotes are at x equals 8 and -2. All right. So the domain is all real numbers except for 8 and -2. Okay, or I could say -infinity to -2, and then from -2 to 8, and then from 8 to infinity. Right, that big U there means union. I'm saying take this line interval and union it with these others, right? Or I could say x can't be 8 and x can't be -2. Okay. Look at these. So this one here, I can factor the bottom as x -2 times x +2. So the vertical asymptotes are at x equals positive or -2. Okay, so the domain is all real numbers except for positive -2. Or I could say -infinity to -2 union -2 to 2 union 2 to infinity. So that tells us all the numbers I can plug in to this function where I get something back, right? As long as I don't get 0 on the bottom, any other number, this is going to spit a number out. So this one over here, I'll factor out an x. I get 8 minus x. So obviously the vertical asymptotes are at x equals 0 or x equals 8. I can't plug in either of those numbers. So the domain would be all real numbers except for 0 and 8. Or I could say -infinity to 0 union 0 to 8 union 8 to infinity. Or I could say x can't be 0 and x can't be 8. Over here, I could have said x can't be positive or -2. Right, so domain. All right, the domain is the exact opposite of where the vertical asymptotes are, right? Asymptotes are that dotted line where the function can't cross. All right, a vertical asymptote at x equals 10. Write a rational function that satisfies the requirements. So I could say f of x equals 1 over x minus 10. Right? That's a simple function. You can't plug 10 in. You get a vertical asymptote there. This one says vertical asymptotes at -5 and 2. Okay, well, how about this? 1 over x plus 5 and x minus 2. If I put a -5, I get 0 on the bottom. If I plug in a 2, I get 0 on the bottom. Boom, can't have that. So here they're saying domain not x not equal to positive -5. So basically that means there's asymptotes at positive and -5. So I could do this, x minus 5 times x plus 5. All right, this function, I can plug in any number I want except for 5 or -5. All right, let's look at big old word problem here. Heavy metal contaminants in a cement quarry may be removed from the soil by planting sunflowers. Use the following model to estimate the number of sunflowers, S in thousands, needed to remove P% of the contamination. Note that P is a percent, so 25% means P equals 25 here. Okay. So how many sunflowers would it take to remove 50% of the contamination? Well, we replace P with 50, 90 over 100 minus 50, which would be 90 over 50, right? Which is 9/5. My phone. I'll put that in a decimal for fun. 9 divided by 5. This is 1.8. So S is in thousands. So we're looking at 1,800 sunflowers. 1,800 sunflowers would get rid of 50% of the contaminants. What about 99%? So if we want to get rid of 99% of the contaminants, we get 90 over 1, which is 90. So 90,000. That's a lot more than 1,800, right? 90,000 sunflowers. What percent removal cannot be achieved? 100. You can't put 100 there. If you put 100 there, you get 0 on the bottom of the fraction. So what it's saying is it's impossible to get all the contaminants out no matter how many sunflowers you plant. That makes sense? You can't put 100 here. Get 0 on the bottom of the fraction. So you according to this formula, you cannot get 100% of the contaminants out of the cement quarry, no matter how many sunflowers. Why not? Can't divide by 0. Okay, you get unhappy face. All right, let's look at number 9 here. Looking at this thing, I can't put a 2 right there, right? Before I even read the problem, I cannot put a 2 right there. I'd be dividing by 0. Oops. So it costs money to keep our lake at Northwest Vista College clean. Say there are 2 tons of pollution in the lake and the cost C in hundreds of dollars removing X tons of pollution is given by C of X. How much would it cost to remove half a ton of pollution? Well, since X is in tons, I put a half here. 70 times a half over 2 minus a half. So this would be what, 35 over 1.5, which would be 3 halves. So this would be 70 over 3. And let's see, 70 divided by 3, 23.3. And this is in hundreds of dollars. So this would mean $23,333 to remove a half a ton of pollution. If they tried to remove all 2 tons of pollution, what would happen? NVC would go broke because it would cost an infinite amount of money. All right. This thing goes to infinity as X approaches 2. That's shortcut calculus notation. So this thing goes to infinity as P approaches 100. Another way we'd say that, we'd say the limit of C of X is infinity as X approaches 2. That's more official notation we teach you in calculus. All right, number 10. The typical round of golf is 18 holes, where your cumulative score for the round is the sum of all shots you took on each hole. If you took 4 shots on each hole, your score is 4 times 18 is 72. So describe the relationship between the rounds of play and the score on 18 holes. So the more you play, the better your score, right? So this is how many times you play. All right. And then here's your score. So what it's saying here, let's see, the score gets bigger and bigger, right? The less times you've played. So this will go down, 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 all right? So if you've only played like once, your score is going to be like 1,000, okay? But the more you play, the smaller your score gets. And there's an asymptote here, not an isotope, an asymptote at 18, right? The best you can get is 18, a hole in one on every single hole, right? So typically this really isn't an asymptote because this thing would touch 18, because in theory you could actually score an 18, right? There's 18 holes. All right, so it's not a perfect example here, but basically that never, ever, ever, ever happens. So again, the more you play, the closer you're going to get to a hole in one on each shot. Homework. Do your homework. All right. Exam time. All right. All right. Well, let me pick some out here then. These will be easy.
You enjoy doing math.
Yeah. I wouldn't be a mathematician if I didn't enjoy doing it. That one, word problems are too long. I can't copy and paste these easily. So we'll do some easy ones then. So this is exam number 23. Is that right? 23. So these should take you like 2 minutes to do. Number one. Oop. And number two. This page 164. There you go, folks. All right. So remember, the vertical asymptote is where you get 0 on the bottom. The domain is all real numbers except where when you get 0 on the bottom. And that's it for today. All right, zoom out.